Hello, my name is Selena Noltenius, and this is Lab 22, Resistivity and Ohm's Law, and this is experiment number 2, Resistance of Playdough. So, as an intro to this lab report, the report looks into the resistivity of materials. In experiment 2, the resistance of Playdough was investigated along with the effects of its length and cross-sectional area. The results verified the hypotheses that resistance rises with length and falls with cross-sectional area. These investigations bolstered theoretical ideas and offered useful insights into electrical characteristics. So as you can see here in the screen, the materials that I used were 3 alligator clips, 2 AA batteries, a AA battery holder, Play-Doh, aluminum foil, a ruler, a vernier caliper, a digital multimeter, and scissors. And this is 2 pictures, one with myself in it and the materials, and one with the materials only. So this is the first part of the experiment, which is the relationship between resistance and length. So in these next few videos, you'll basically see a, an experimental setup for testing the relationship between resistance versus length. And then we'll see how the experimental setup is put together to see the resistance versus area part of the experiment. As you can see, I have already turned my multimeter on to the 20 mark here. The cords are set to the places that they're supposed to be, as you can see. And then I have already placed my batteries inside of the battery holder with the negative sides of the battery close to the spring end of the battery holder. And here I have all of my other materials. Right now I'm going to show you how we measure the voltage of the battery. So we grab our 2 cords and we measure and see how much the voltage is. So I'm getting a 3.21 number. Yes, 3.21. As you Now I have, as you can see, I have my Play-Doh here. I measured it and I first formed it into a cylinder that is 20 centimeters in length. So as you can see, it's 20 centimeters, as you can see. And then I used this to measure its diameter, which is approximately 10 centimeters all the way. So this is what we got right now. So right now the circuit looks like this. The cylinder has a length of 20 centimeters. Then the positive side of the battery holder is connected to one of the aluminum rods. And then the negative side of the battery holder is connected to the black probe of the multimeter. And then the third alligator clip connects the red probe of the multimeter. And now I'm going to connect it to the right end of the aluminum foil and wait for 10 seconds to see if any current appears. So right now the right aluminum foil has been moved 2 centimeters to the left, and I'm going to see how that affects the amperes in the multimeter. So we're going to connect it here like this, and then I'm seeing how it is a higher number in the multimeter, as you can see. So I'm reading about 1.40 and then disconnected after about 10 seconds. So this is part two of the experiment, which is measuring the relationship between resistance and area. So now we're doing part two of the experiment, which is the relationship between resistance and area. As you can see, I have already set up my circuit, very similar to the last part, to part one, where my circuit looked like this. Um, and I want to show you that right now, the length of the cylinder is much more, um, it's much less longer. So it's between 10 to 12 centimeters, which is, and that's the length. And the diameter is going to be approximately between 10 to 15 millimeters. So right now I'm going to connect this, the right aluminum foil to this end of the alligator clip, which is connected to the red probe of the multimeter. And my multimeter is in 20 for the DCA portion. And I'm going to connect it like this and wait to see what does. And I'm going to wait for 10 seconds approximately as my multimeter changes. It, it keeps on changing. And right now, this is the setup. And then after 10 seconds, I get this off. I have now remolded my cylinder for it to have a different area. So that means that it's going to have a different diameter. I chose a smaller diameter this time, and now we're going to see how it affects the number in the multimeter. So if we connect this here, like this, and leave it for 10 seconds, it starts to change, and we wait 10 seconds for it to give us a final reading. I So as seen by the results, here you can see the diameter column, the area of the cylinders formed with the Play-Doh, the currents that I was getting, and then the resistance that I calculated. And here you can see the relationship between resistance versus length. So as shown by the graph, the resistance of a conductor is directly proportional to its length. This relationship is described by the formula R equals Q times L over A, where Q is the resistivity of the material and A is the cross-sectional area. In this experiment, as the length of the Play-Doh is kept constant, the resistance should not vary with length. However, if we vary the length, we would expect the resistance to increase linearly with the length. And here you see the relationship between resistance versus area. The resistance of a conductor is inversely proportional to its cross-sectional area. In this experiment, as the cross-sectional area of the Play-Doh increases, the resistance decreases. This inverse relationship means that if the cross-sectional area is doubled, the resistance is halved, assuming the length remains constant, of course. The data collected and plotted shows that as the area increases, the resistance drops significantly, confirming the expected theoretical behavior. So, thank you.